All right, so last time I said we were going to jump ahead to slide 23, and that's what we're going to do. So we're going to talk about absolute, oops, and relative configuration and absolute relative configuration is something that comes up, well, absolute conformation comes up a lot more in the lab when you're thinking about a molecule that you've made than it does like in class, right? In paper, we can know the absolute configuration. So absolute configuration is when R or S is known exactly. So you might be thinking, well, of course it's known exactly. I drew it that way, right? I drew there's math, R isomer. So of course I know the configuration. But absolute configuration really talks more about like when you're in a lab, right, and you make a molecule, how do you determine if you have R or S? How do you know absolutely if you have the R enantiomer or the S enantiomer? So absolute configuration is when you can make a molecule and then determine that you have R or S. So the ways to do this are usually a little more complicated than figuring out relative stereochemistry. So one way to figure out absolute stereochemistry is via X-ray. So when you hear X-ray, you think like broken arm, take a picture of your arm, right? See the bone. For molecules, it's a little different, but it's similar. If you can get a molecule to be crystalline, if you can get it to be a crystalline solid, you can shine an X-rays through that molecule, and the X-rays will actually hit the atoms or the electron clouds around the atoms and scatter and make a pattern. And we can take that pattern, run it through a computer, and it will actually spit out where every atom is in the molecule. So if you have the right kind of crystal, you can use X-ray to determine R and S. You have to have a really big group on there, like a bromine, but you can figure out R and S from that. Um, so for someone like me, my job would be to make the crystal, and then there's usually some little hobgoblin that lives like down in the basement, and you're like, sir, please tell me what this is. You like, maybe you like slide him $5, and then you're like, and you come back and he just gives you like a sheet. It's just a picture, and you're like, oh, cool, thanks. It's basically just taking a picture of your molecule, and it shows you where everything is. And then there's like 25 pages of data that you go, nah, I think I got the picture, right? So you can do X-rays, or you just zap your molecule and you get a picture of it. And then another way that you can do this is you can uh, convert your molecule to a known molecule, where that known molecule you've already determined, or someone has already done all the really hard work to figure out if it's R or S. And then you can just use like optical rotation to see if you match, right? So let's say you made this and you wanted to know if that chiral center was R or S, right? You don't know, so you can convert it to something that is known, like lactic acid. And then you can say like, oh, the optical rotation for lactic acid is known, right? It's plus 80, let's say. Well, my lactic acid that I made is minus 80. So that means if lactic acid is R, I must have the S enantiomer of my thing, right? So you can figure out this compound, the one that you made, and then use that to say, like, this chiral center didn't change. So now I can figure out the R or S of what I started with. All right, so that's absolute configuration, is when you're done, you can say, this thing I have in this flask is the S enantiomer, or it's the R enantiomer. You know 100%. So this doesn't really apply to like in class because you just draw it, right? But in lab, you have to actually figure that out. The other type of configuration is relative configuration. And relative configuration is your stereocenters are assigned based on other groups in the molecule. Oops. I'm trying to kind of define it without saying they're relative to each other, right? So you don't know 100% if you have R or if you have S for your chiral centers, but what you do know is, hey, these two groups are on the same side or they're on opposite sides. So relative configuration comes down a lot of times to being cis or trans, things on the same side or things on opposite sides. So, like, what this means is, let's say we have this molecule. This is the cis isomer, right? The OH and the methyl group are on the same side. What you don't know with relative configuration is you don't know if they're both up or, oops, as he draws the same thing, or if they're both down. What you know is they're on the same side, right? So you know they're cis, you know they're on the same side, but you don't know if it's a wedge or a dash, right? So you know them relative to each other, but you don't know absolutely if your OH is R or S. You just know, hey, it's on the same side as the methyl. Where like trans, you know they're on opposite sides, but you don't know which one's the wedge and which one's the dash. All you know is they are across from each other. So that's relative configuration, is I know that these are on the same side or on opposite sides, but I don't know if they're up or down. Make sense? Okay, we were at 17 Zoom people, and we hit 9. 26 people. Whew. Whew. And these YouTube videos are carrying some people, apparently. Which is cool, whatever, man. So we're going to talk about a concept called prochirality. It's the next thing on the list. Prochirality, I like to say this is a carbon or group, or carbon, or I guess atom, that is almost chiral, which is kind of a weird thing to think about, being almost chiral. So normally, or this is going to be, it's going to have 3 groups, or 3 different groups. Bonded to a carbon. So if you change one of the groups that's identical, you go from being almost chiral to being chiral. So the example I use is ethanol. This carbon is prochiral. If I were to change either one of those hydrogens to basically anything that's not an OH or a methyl, I'm going to end up making a chiral carbon, right? So that carbon is prochiral. It's almost chiral. Just making a small change would make it chiral. The change we make with prochiral carbons is we will change so we're going to change an H to a D. We're going to change a hydrogen to a deuterium. Right? Deuterium is just heavy hydrogen. It's hydrogen with one extra neutron in it. So it is the smallest possible change you can make to a molecule or make to a hydrogen, right? So if I change this H to a D, now I have a chiral center, right? This carbon has gone from being prochiral to being now this is chiral. And I can change the other hydrogen to a deuterium. Right, so just making that small change, effectively adding an extra neutron to your hydrogen, takes this carbon from being not chiral to being chiral. So, before we go through all the rigmarole, why does this matter? Why do we care that carbons can be almost chiral? Again, we will use ethanol as our example. So, and we're going to go into like biology for drunk toddlers, like not deep or anything. It's going to be pretty rough. But when you drink alcohol, your body removes a hydrogen from alcohol, or two hydrogens actually, and oxidizes it to an aldehyde. So this carbon right here had two hydrogens on it. Now it has one, right? The enzyme that does this is alcohol dehydrogenase, whatever, right? But the thing that matters here is when you have a compound that has a prochiral center, if it interacts with something chiral, those two carbons, or sorry, those two groups, in this case, these two hydrogens here, these two hydrogens, are going to be seen as being different by the chiral thing they're interacting with. So alcohol dehydrogenase actually 100% of the time only removes one of those two hydrogens. So let's say the way I have it drawn, it only removes this hydrogen. So you've got your alcohol. It's in the enzyme. I'm going to make all the biology people feel at home. Just like a little blue crescent, right? There you go. Enzyme. Boom. Right? And the thing that grabs that hydrogen is always, the group that grabs the hydrogen is always closer to the hydrogen that's on the wedge, the way I have it drawn, right? So every single time alcohol binds to that enzyme, this is the alcohol, this is the hydrogen that we remove. We need some way to like clearly communicate which hydrogen is the hydrogen that we're removing, right? We can't just say, the wedgie one when the OH is drawn to the right. Hey, that does not sound very scientific at all, right? Because what if I draw the hydrogen to the left, the OH to the left, and it's like, oh, it's the dashy one now, right? So what prochirality does is it lets us assign a basically like a name to each of those hydrogens. So we can say this specific hydrogen is the one that is being taken. So, getting this in a slightly different order than the slides, but whatever. So we can assign hydrogens as being pro-R or pro-S. So if changing your hydrogen to a deuterium leads to an R chiral center, your hydrogen was pro-R. If changing that H to a D leads to an S chiral center, your hydrogen's pro-S. Right? So we can take our almost chiral carbon, change a hydrogen to a deuterium, assign R and S, and then say the hydrogen that was on that molecule was pro-R or pro-S. If we made that hydrogen anything else, it became R, so that hydrogen's pro-R. So one thing you need to do when you're doing prochirality is you need to kind of label your hydrogens that you start with. I like to use A and B. Okay. As long as you're consistent when you do this, it doesn't matter which one you make A and which one you make B. If you made the dash A and the wedge B, as long as you were consistent throughout doing it, doesn't matter. So let's say we turn HA to a deuterium. Now we can assign R and S to this. Sorry, move my thing. 1, 2, 3. Deuterium gets priority over hydrogen because it's heavier. So is this R or S? R. So since changing HA to a deuterium made an R chiral center, we can say that HA is pro-R. Right? Now if we change HB to D, oops. Right? Now, I'm hoping you can guess what this is already. Right? This looks R, but it is S. So now we can say that HB is pro-S. So what this lets us say is instead of, the wedgie hydrogen, right, we can say, oh, alcohol dehydrogenase removes the pro-R hydrogen from ethanol during the oxidation. So now you could just look at an ethanol and figure out which hydrogen is pro-R and which one's pro-S, and then know which hydrogen gets removed by that enzyme. So these two compounds, are they enantiomers or are they diastereomers? They are enantiomers. So these two compounds are enantiomers. So if changing the groups on your prochiral center makes enantiomers, right? So if changing the groups on your prochiral carbon make enantiomers, the groups are enantiotopic. So if changing HA to a deuterium makes one enantiomer, and changing HB to a deuterium makes the other enantiomer, those two hydrogens were enantiotopic. The shorthand is like you have a prochiral carbon with no other chiral carbons. So if you have a molecule that has no chiral carbons and a prochiral carbon, the groups on that prochiral carbon are going to be enantiotopic. If changing the groups on the prochiral carbon makes diastereomers, those groups are diastereotopic. Right, the shorthand here, you have a prochiral carbon with at least one chiral carbon. So your molecule has at least one chiral carbon in addition to your prochiral carbon. That means that you're going to make diastereomers when you change your groups, when you change your H's to D's. So then those two groups are diastereotopic. So how many prochiral carbons are in this molecule? One. We have one right here, right? This carbon here on its two hydrogens. And if I changed either one of those hydrogens, I'd make a chiral center. Are these two groups enantiotopic or diastereotopic? Does changing them make enantiomers or make diastereomers? Diastereomers, right? So these two groups are diastereotopic. Right, so if I went like A, B, I could have right, you can see that those two molecules, when I changed the hydrogens, when I changed, right, HB stayed the same, and HA became a deuterium. HA stayed the same, and HB became a deuterium. You can see that these two molecules are diastereomers of each other, right? One chiral carbon stayed the same, right? This methyl group stayed a wedge. The other chiral carbon changed, right? You switched the H in the deuterium. Make sense? Seem reasonable? What if you had I'll do like that. There you go. How many prochiral carbons does this molecule have? really ugly hexane. It actually has a bunch. It's got this one and all of those. Because each of those I could change a hydrogen on and make it a chirocarbon. We're going to focus on this guy though. Right, so it has like 6 prochirocarbons. But, okay. If we were to change the hydrogens on this to deuteriums, would I make enantiomers or would I make diastereomers? I'd make enantiomers. So that means these 2 hydrogens are enantiotopic. So what I want you to be able to do would be to look at a molecule, figure out how many prochirocarbons there are. This was not the greatest example. Usually I'll keep it to like 1 or 2, right? Not like a bajillion, right? 2, be able to determine if the groups on that prochirocarbon are enantiotopic or diastereotopic, which basically what I'm asking you is there a chiral center already in this molecule? If no, enantiotopic. If yes, diastereotopic, right? And then I would have to actually draw the structure. Like I would have to give you, whatever. I would have to draw like HA, HB, and then say like, hey, which of these 2 groups is pro R, right? HA or HB, right? But I'd have to label it for you because you could easily, if you did it yourself, right? The labels don't matter. You could easily go like HA, HB, and it would still work, right? So I'd have to like label which one's HA and which one's HB, and you could tell me which one's pro R, which one's pro S. They should be able to identify prochirocarbons if they're enantiotopic or diastereotopic, and then if kind of given the right kind of problem, then assign them pro R or pro S. That's what I want you to get out of this. And I want you to know that it matters because when achiral things interact with chiral molecules, the chiral molecules will be able to like determine what that they have assigned. Everyone good?
I was asked to clarify when groups are enantiotopic or diastereotopic.
Yep. So because when you change these groups, let me do a simpler one. Let me just do the one I just drew. Right? So when I change HA and HB, right? When I change those to deuteriums, these 2 molecules are enantiomers. So that means changing A and B makes enantiomers. That means they're enantiotopic. So the shortcut for it is if there's a chiral center already in the molecule, changing those groups makes diastereomers. So that's why you can just kind of say like, is there a chiral center here already? No. Changing those groups make enantiomers, so they're enantiotopic. Is a chiral center, changing those groups makes diastereomers, so they're diastereotopic. So basically, you can just draw the 2 molecules you get from replacing your hydrogen with deuterium and then say, hey, are these enantiomers or diastereomers? If they're enantiomers, enantiotopic. If they're diastereomers, diastereotopic. That make more sense? Excellent. Okay. So, way back in a simpler time, exam 1, right? we went over cyclohexanes that had one thing on them, right? And we knew that the chair conformation that was preferred was the one that had the one group equatorial. Now we're going to start talking about chair conformations that have two groups on them, right? So we know this, right, because we're very smart. That ignore the fact that one is very fat and one is very skinny. I'm sorry. Right? But we know that we favor when our one substituent on our chair is equatorial. So this is favored. Because our group is equatorial. So now we're going to start throwing extra stuff on our ring. And we're going to have to figure out how we know which conformation is favored. Right, so we're going to do conformations of, that's not even going to fit, disubstituted cyclohexanes. Right. So here, the size of the groups that we have on the ring matters. The general rule of thumb is the big group is going to be the group that is equatorial. So we need to look at our two groups that we have on our ring, decide which one is bigger, and then that is the group that ends up being equatorial. So basically I have 4 groups that I need you to know in terms of size. So tert-butyl is the largest group that you're going to have. That is bigger than isopropyl. Oops. Which is bigger than ethyl, which is then bigger than methyl. So tert-butyl is your largest group. Methyl is your smallest group. I want to point out here that ethyl is doing a lot of work here. This is a standard for all straight chain alkyl groups. So basically, there's really not a difference in size between ethyl, propyl, butyl, pentyl going all the way up, right? The size, the bulk that matters is the bulk that is close to the cyclohexane. So if you have a decane, carbons like 4 through 10 are so far away from the ring, they never really interact with the ring, right? So we just basically have to lump all of our straight chains and say they're as big as ethyl. Because once we get past like a couple carbons, that stuff's too far away to matter. Okay. So even if you don't like have any sense of kind of what's going on, right, you can look at a cyclohexane, you can look at a chair. Which one of these two groups is favored? Okay, so basically I'm asking which is bigger, isopropyl or methyl? A. So isopropyl is bigger, thus it wants to be equatorial. So this would be favored. So you have to look at these and go, okay, which one of these groups is bigger? And that's the one I want to be equatorial. Tert-butyl can never be axial. It is too big to be axial ever. So you never draw just a cyclohexane with an axial tert-butyl group. So why does this size thing matter? How does this size stuff work? Right, if you remember, you have your methyl group, right? When you have a group that's axial, you have a destabilizing interaction between the axial groups that are on the same side of the molecule, right? You have A13 interactions. I made it through the whole first class and didn't cough once. Right. So as your groups get bigger, those A13 interactions increase, right? So methyl, you're pretty far away from the hydrogens. If you go to ethyl, oops, make it black. If you go to ethyl, right, your A13 interactions are stronger because, right, the methyl group at the end of the ethyl kind of points over the ring and gets closer to those hydrogens. But as we know from drawing Newman projections, that ethyl group isn't stuck with the methyl group sticking out over the ring, right? It can rotate. So right, a lot of the time, that methyl group's going to turn away and point away from the ring, right? So it's not going to have such a strong interaction. Now, if I go from methyl to isopropyl, I now have two methyl groups. So there's twice as much time that there's going to be a methyl group sticking right over the ring. Make sense? When you go to tert-butyl, there's three. Now, no matter how you draw your tert-butyl group, how you rotate it, there's always a methyl group sticking right over the ring, jamming itself into those hydrogens and being destabilized. So as you add more groups, you spend more time with a group of some sort stuck into the ring and banging into the other axial groups. So that's why, like, if I had a propyl, right, I just add that methyl group's kind of out of the way. Butyl, they just get further and farther away. That's why it doesn't matter why ethyl gets to stand in for everything. because we really just care about that first carbon off the methyl group. How we doing, Zoom? So far, so good? All right.
I was asked to explain what I meant by like adding more groups or adding more methyls to something.
Yes. So here, I'll show you real quick. So I'll draw it like this. So you add more groups. Let's say you're an ethyl, and you have sometimes that methyl group on your ethyl is sticking in over the ring, right, and bangs into those hydrogens. But there's also an awful lot of time where that hydrogen is sticking away from the ring. That makes sense? Now let's say I have an isopropyl. Now I have two groups, right? So there are less conformations that I can have where I don't have a hydrogen or don't have a methyl group jabbed over the ring. So if I drew it like this, here's my hydrogen. So I kind of have one conformation where I can like put the methyl groups away from the cyclohexane and have a hydrogen sticking back in. When I have a tert-butyl, which requires me to go to another slide, there's no conformation that I can draw that doesn't put a methyl group jabbed back into the ring, right? If I drew it like with wedges and dashes. Because I was like, oh, hey, this is awful. Right, no matter how I turn around that ring, every time I turn it to like make a new Newman projection, I'm going to have a methyl group that sticks back into these hydrogens. So when it's a methyl, you just have three hydrogens. Ethyl, you have two hydrogens in a methyl, so you can kind of sometimes hide your methyl group away from the ring. Isopropyl, you have two methyls in a hydrogen, it becomes harder to hide your methyl groups. Tert-butyl, now there's three methyl groups, there's nowhere to hide. You're always going to have a methyl group stuck, like jammed right towards those hydrogens, banging into them. That's what I mean by as you add more groups to that like methyl group, you go from methyl to ethyl to isopropyl to tert-butyl. It just becomes you have more and more times where you have a methyl group where you have a group pushed back into the other axial group. Good? Okay. I was gonna say if I stand there long enough, they might think I just froze. I used to do that in YouTube videos. I would just like go, or like I would just be like, now think about this, and just stand and not move. Okay. So we got to have that down. I want to go through the different types of cyclohexanes, the different substitution patterns that you can have on a cyclohexane, and kind of show you some of the tricks for them. And we're only going to get like started on one, and we'll finish up the other two on Monday, and we'll pick up on like what's it called on alkenes. So I'm going to start with 1,4-disubstituted. Right, so you have groups on opposite sides of the cyclohexane. Right. So the first thing to notice here is there's a plane of symmetry. Right. So there's no chiral centers. It only has cis and trans, right? You only have relative stereochemistry. The groups can either be on the same side of the molecule or they can be on opposite sides of the molecule, and that's all you have in terms of stereochemistry. So you can have methyl group up, tert-butyl group up, that's cis. That is exactly the same as methyl group down, tert-butyl group down, because you can just take that molecule and flip it over, and it's the exact same thing, right? So wedge is the same as dash dash. Or you can have trans, one wedge, one dash. Now I want to show you real quick, just the start of how you go from these skeletal structures to drawing a chair. And I'm going to kind of leave you on that to stew about, and then we'll pick that up on Monday. So if you have a cyclohexane, well, move it. If you have a chair, I like to think about this hydrogen here, this axial hydrogen. I like to say that it's up and corresponds to a wedge on the skeletal structure. And that makes sense. Wedges are up. Clearly, this hydrogen is pointing straight up on this ring. Now, all your axial groups then alternate around the cyclohexane. This hydrogen is down. This one is up, down, up. This one's a little hard to draw. And this one is down. So we can use that to actually go from the skeletal structure to the chair structure.